124 light-years from here, there is a planet that might be covered by a single, uninterrupted ocean, wrapped in a thick blanket of hydrogen, orbiting a small, dim star in exactly the zone where water could stay liquid. In 2023, a space telescope found methane and carbon dioxide in its air. In 2025, the same telescope found something stranger, faint traces of a gas that, on Earth, only comes from one place. Living things in the ocean breathing. This week, a different set of instruments turned toward that same planet, not to look at its light, but to listen. Two of the most sensitive radio observatories on Earth spent 33 days, an entire year on that distant world, quietly recording every signal arriving from its direction, checking for the one kind of noise nature almost never makes on its own. Tonight, we're going to walk through exactly what they were listening for, exactly what they heard, and exactly what it means that, after scanning millions of individual signals, they still can't tell you, for certain, whether anyone is out there. This is the real story of K218b, and it's stranger and quieter than the headlines let on. If you find yourself drawn into stories like this one, take a moment to like this video or subscribe. It helps more than you'd think, and it lets us keep making these late night trips together. Now, let's begin. Let's start with the basics, because K218b has been in and out of headlines for years now, often without enough context to actually understand what's being claimed, or how much weight any of it should carry. K218b is an exoplanet, a planet orbiting a star other than our own Sun, first discovered in 2015 through observations from the Kepler Space Telescope, and later confirmed and studied in greater detail by the Hubble Space Telescope, and most significantly, the James Webb Space Telescope, or jwst, which launched in December 2021 and represents the most powerful space-based observatory ever built for studying the atmospheres of distant worlds. K218b orbits a small, cool star called K218, classified as a red dwarf, located in the constellation Leo at a distance of approximately 124 light-years from Earth. To put that distance in context, using the same kind of comparison we've used before on this channel, light itself, travelling at roughly 186,000 miles per second, the fastest speed anything can travel, according to everything we currently understand about physics, takes 124 years to make the journey from K218 to Earth. Every photon of starlight astronomers have ever used to study this planet left its star before either of your grandparents were likely born, and has been travelling, uninterrupted, through empty space for over a century, just to arrive here. In terms of physical size, K218b sits in a category of planet that doesn't exist anywhere in our own solar system, which is part of what makes it so genuinely interesting to study. It's classified as a sub-Neptune, larger than Earth but smaller than Neptune, with a radius estimated at roughly 2.6 times that of Earth, and a mass around 8.6 times Earth's mass. We have no direct analogue for this kind of world close to home. Earth and Venus are rocky and relatively small, while Neptune and Uranus are enormous ice giants many times larger. Sub-Neptunes like K218b occupy a strange, poorly understood middle ground, and remarkably, current surveys suggest this category of planet may actually be one of the most common types of planet in the entire galaxy. even though our own solar system doesn't have a single example of one. What makes K218b specifically compelling, rather than simply another data point among the thousands of exoplanets discovered so far, is where it sits relative to its star. K218b orbits well within what astronomers call the habitable zone, the region around a star where temperatures could, in principle, allow liquid water to exist on a planet's surface, neither so hot that any water would boil away into vapour, nor so cold that it would freeze solid. Because K218's star is a red dwarf, much smaller, cooler and dimmer than our own Sun, its habitable zone sits much closer to the star than ours does. K218b completes a full orbit around its star in just under 33 Earth days, which is why. When astronomers this week wanted to observe the planet for one complete orbital period to search for any periodic radio signals tied specifically to its motion, they only needed to watch for 33 days, rather than the 365 days a similar search around our own Sun would require. In 2023, a research team led by astrophysicist Niku Madhusudhan at the University of Cambridge published jwst observations of K218b's atmosphere that generated genuine, widespread excitement across the scientific community. Using jwst's near-infrared spectrograph, the team detected clear signatures of methane and carbon dioxide in the planet's atmosphere. At a statistical confidence the team described as 5 sigma for methane and 3 sigma for carbon dioxide. Thresholds generally considered strong evidence in physics and astronomy, though we'll return shortly to exactly what those numbers do and don't guarantee. Critically, the team did not detect ammonia, a gas that models suggested should be common in a hydrogen-rich sub-Neptune atmosphere at K218b's temperature, unless something was actively removing it, potentially a vast, planet-covering ocean of liquid water beneath the hydrogen envelope, since ammonia dissolves readily in water. Based on this combination of findings, methane and carbon dioxide present, ammonia conspicuously missing, Madhusudhan's team proposed that K218b might be what they called a Hycean world, a term the team itself coined, combining the words hydrogen and ocean, describing a hypothetical class of planet covered by a global liquid water ocean, sealed beneath a thick, hydrogen-rich atmosphere. It's worth taking a moment to explain exactly how a telescope, sitting roughly 1 million miles from Earth, can determine the chemical composition of an atmosphere on a planet 124 light-years away. Because the technique itself is almost as remarkable as anything it's actually found. jwst doesn't photograph K218b directly in any conventional sense. The planet is far too small, far too dim, and far too close to the overwhelming glare of its own host star for any current telescope to simply take a clear picture of its surface. Instead, astronomers use a technique called transit spectroscopy, which relies on a specific favourable alignment. From Earth's vantage point, K218b happens to pass directly in front of its host star during each orbit, an event called a transit. During that transit, a small fraction of the star's light passes through the outer edges of the planet's atmosphere on its way to Earth, rather than being blocked entirely, and different molecules within that atmosphere absorb very specific, precisely known wavelengths of light as it passes through, leaving a kind of chemical fingerprint embedded in the starlight that eventually reaches jwsts. instruments. By carefully measuring exactly which wavelengths of light are slightly dimmer during a transit compared to when the planet isn't transiting at all, and comparing those measurements against laboratory-verified absorption patterns for known molecules, astronomers can identify which gases are present in the planet's atmosphere and estimate roughly how abundant each one is, without ever needing to send a single probe anywhere near the system itself. This technique, while extraordinarily powerful, is also inherently limited by the physical realities of the method. The signal being measured, the tiny difference in starlight caused by a thin ring of planetary atmosphere passing in front of an enormous, blindingly bright star 124 light-years away, is extremely faint, and every single molecular detection reported for K2-18b, including the confirmed methane and carbon dioxide, and the disputed dimethyl sulfide, has been extracted from data sitting right at the edge of what jwst's instruments can reliably measure at all. This is precisely why the DM's controversy discussed shortly exists in the first place. It isn't that different research teams disagree about basic physics. It's that they're all working with a genuinely difficult, noisy, borderline signal, and reasonable, competent scientists can and do reach different conclusions about how to interpret data this close to the edge of detectability. And then, tucked inside that same 2023 announcement, almost as a footnote to the more confidently reported methane and carbon dioxide detections, the team mentioned something else, a faint, low-confidence hint of a molecule called dimethyl sulfide, often abbreviated DMs. On Earth, DMs is produced almost exclusively by marine phytoplankton and algae, released into the atmosphere through their ordinary biological processes. And it breaks down quickly once released, meaning any detectable atmospheric concentration generally has to be actively, continuously replenished by living organisms. Because of this, astrobiologists have studied DMs for years as one of the more promising potential biosignature gases, a chemical fingerprint that, if detected on another world in sufficient quantity, would be difficult to explain through any known non-biological process. The 2023 detection was weak, only about 1 sigma of statistical confidence, far below any threshold anyone would consider reliable on its own. But it was enough to make K2-18b, already interesting for its methane, carbon dioxide, and potential ocean, into one of the most closely watched exoplanets in the world. It's worth understanding a little more about dimethyl sulfide itself, and why scientists became so interested in this specific molecule as a potential biosignature in the first place, rather than any of the countless other chemicals that might theoretically indicate life. On Earth, DMs is produced through a specific biological pathway, marine phytoplankton. Microscopic photosynthetic organisms that form the base of most ocean food chains produce a related compound as part of their normal cellular processes, which is then broken down by other microorganisms and released into the atmosphere as DMs. It's genuinely difficult to produce DMs through any known non-biological, purely geological or chemical process in significant quantities on Earth, which is exactly what makes it scientifically interesting as a potential biosignature, unlike oxygen, which can, under certain unusual planetary conditions, be produced abiotically without any life involved at all. DMs in Earth's own atmosphere is, for all practical purposes, exclusively a byproduct of living organisms. But exclusively a byproduct of life, on Earth is a meaningfully different, more limited claim than exclusively a byproduct of life anywhere in the universe. And this distinction sits at the heart of why the DM's debate has remained so genuinely contested. Researchers have pointed out that DMs has in fact been detected in at least one place with no biological connection whatsoever, on comets within our own solar system, including detailed measurements taken during the European Space Agency's Rosetta mission to comet 67P Churyumov-Gerasimenko, where DMs was identified as one of many organic compounds present in the comet's composition, produced through entirely abiotic chemical processes involving no life at all. This finding doesn't rule out a biological origin for any DMs potentially present on K218b, but it does complicate the simple, appealing narrative that detecting DMs anywhere in the universe automatically points to life, since we now have direct, confirmed evidence that at least some non-biological pathway to producing this exact molecule genuinely exists. The chemist Nora Hinney of the University of Bern, whose own research helped establish the comet-based DM's detection, has described the molecule as, in her words, a clean, unambiguous biosignature, specifically in the context of Earth's own atmosphere, where scientists understand the full local chemistry and can rule out competing explanations with confidence. Extending that same confidence to an atmosphere 124 light-years away, on a planet type with no direct analogue anywhere in our own solar system, orbiting a star fundamentally different from our own Sun, requires a much larger and much more uncertain leap, one that the scientific community, quite appropriately, has been unwilling to make without significantly more evidence than currently exists. 2 years later, in April 2025, Madhusudan's team returned with new data, this time using a different jwst instrument, the mid-infrared spectrograph called MIRI, observing K218b at longer wavelengths than the original 2023 study had covered. This new observation reported a stronger signal, still not definitive, but reaching roughly 3 sigma confidence, consistent with either DMs or a closely related molecule called dimethyl disulfide, sometimes abbreviated DMDs. According to the team's own calculations, the concentration implied by this signal would need to be extraordinarily high, potentially thousands of times greater than the concentration of DMs found in Earth's atmosphere, an amount that, if the detection holds up and if the biological explanation is correct, would suggest a planet with an ocean absolutely teeming with some form of life, releasing this gas at a scale far beyond anything our own planet produces. This is the point in the story where the actual scientific process, messy, contested, and far more honest than most headlines allow, becomes just as important as the initial exciting claim itself. Because almost immediately after the April 2025 announcement, other research teams began publishing independent reanalyses of the same JEST data, and the results have been anything but a clean confirmation. Let's walk through what those follow-up studies actually found, because this is where the real texture of scientific uncertainty lives, and it's worth sitting with rather than skipping past. A team led by Jake Taylor questioned the statistical robustness of the original DM's detection entirely, suggesting the signal was more marginal than the initial confidence level implied. A separate team, including researchers Lewis Wellbanks and others, found that the specific set of molecules used in Madhusudan's original analysis was narrowly constrained in a way that significantly influenced the outcome, meaning that expanding the list of candidate molecules considered in the analysis changed how convincingly DMs explained the data. Perhaps most significantly, a team led by Kevin Stevenson, working with NASA-affiliated researchers, conducted an independent reanalysis using their own data reduction and spectral retrieval methods, examining the full transmission spectrum across the entire 0.7 to 12 micron wavelength range covered by jwst's combined instruments. Their conclusion was pointed. While a particular binning method applied to the mid-infrared data could support a tentative DM's or DMD's detection, the same conclusion did not hold up under the majority of alternative, equally valid ways of processing that same underlying data. In their own words, published in their paper's abstract, roughly 87.5% of the reasonable analysis approaches they tested did not support the detection at all. Their broader conclusion was that unaccounted for noise in the mid-infrared instrument, rather than any genuine signal from the planet's atmosphere, was the most likely explanation for the apparent DM's feature, and that, as of their analysis, there remains no statistically significant evidence for biosignatures in K218b's atmosphere. A separate, independent effort, led by researcher Christopher Glein and others, approached the question from a different angle entirely, not reanalyzing the spectral data itself, but instead modelling whether the Hycean Ocean scenario even makes physical sense in the first place. Some of this modelling work has suggested that the temperatures and pressures likely present beneath K218b's hydrogen envelope might be far too extreme to support a habitable liquid water ocean at all, with some models instead favouring a scenario involving a deep, scalding magma ocean, a proposition the planetary scientist Sarah Seeger has described in blunt terms as about as inhospitable as it gets, a description about as far from a thriving alien biosphere as you can get, while still technically using the word ocean. So where does this leave us, honestly, before we even get to this week's radio survey? K218b has real, confirmed methane and carbon dioxide in its atmosphere, detected with reasonably strong statistical confidence. It has a genuinely disputed, low to moderate confidence hint of a potential biosignature gas that some independent teams can reproduce under certain analysis conditions, and others cannot reproduce at all. It sits in its star's habitable zone, but whether habitable zone for this particular kind of planet actually translates into a habitable surface remains a genuinely open, actively contested scientific question, with serious researchers proposing everything from a life-friendly ocean world to a molten hellscape as equally plausible interpretations of the same underlying data. This is not a planet where scientists have found aliens. It's a planet where scientists have found enough ambiguity, enough tantalizing partial evidence, to justify pointing some of the most sensitive instruments on Earth directly at it, just in case. Which brings us to this week, and to a completely different kind of search altogether, one that has nothing to do with atmospheric chemistry, and everything to do with a much older, much more direct question. Is anyone out there trying to talk? The idea that a distant civilization might be detectable specifically through radio signals dates back to a foundational scientific paper published in 1959 by physicists Giuseppe Cocconi and Philip Morrison, which argued, with genuine mathematical rigour, that radio waves represented the most efficient, most physically plausible medium through which an advanced civilization might attempt to signal its presence across interstellar distances. Their reasoning was straightforward. Radio waves travel at the speed of light, cost relatively little energy to transmit compared to other forms of interstellar signalling, and pass largely unimpeded through the vast, mostly empty medium of interstellar space, arriving at a distant receiver largely intact after journeys of decades, centuries or longer. This paper effectively launched the modern scientific search for extraterrestrial intelligence, commonly abbreviated SETI, giving the entire field a specific, physically grounded target to search for, rather than simply speculating in the abstract about whether life might exist elsewhere. The specific kind of signal SETI researchers look for is called a narrowband technosignature, and understanding exactly what that term means is essential to understanding what happened this week. Natural astrophysical processes, stars, pulsars, galaxies, black holes, tend to emit energy across broad swaths of the electromagnetic spectrum simultaneously, a wide, smeared-out signal spanning many frequencies at once, the natural result of chaotic, high-energy physical processes with no organizing structure behind them. Deliberately engineered radio transmissions, by contrast, tend to be narrowband, concentrated within an extremely small range of frequencies, because this is simply the most efficient way to transmit a signal with the least energy waste, whether you're building a radio station on Earth or, hypothetically, trying to signal your presence across a distance of 124 light-years. In practice, this means that if researchers detect an extremely narrow, tightly concentrated spike of radio energy coming from a specific direction in the sky, one that doesn't match any known natural astrophysical process, it becomes a genuinely interesting candidate signal worth investigating further, precisely because nature so rarely produces signals shaped this way on its own. This week's search, formally titled A Narrowband Techno-Signature Search toward the Hycean candidate K218b using the VLA and MeerKAT, and led by researcher C.D. Tremblay, along with a team of collaborators, represents one of the most sensitive, most methodologically rigorous searches of this kind ever conducted toward a single exoplanet system. The team used two of the most capable radio telescope facilities currently operating on Earth, the Carl G. Jansky Very Large Array, commonly known as the VLA, a network of 27 individual radio dishes spread across the high desert plains of New Mexico, each dish 25 meters in diameter, working together as a single, enormously sensitive instrument, and the MeerKAT radio telescope, an array of 64 dishes located in the remote Northern Cape region of South Africa, one of the most sensitive radio observatories in the Southern Hemisphere, and a precursor instrument to the even larger square-kilometre array currently under construction nearby. Both facilities observed the K218 system across an unusually wide range of radio frequencies, spanning from 544 MHz up to 9.8 GHz, and critically, the observations were spread across multiple separate epochs, deliberately timed to cover at least one complete 33-day orbital period of the planet around its star. This detail matters enormously, and it's worth explaining exactly why. If a hypothetical transmitter were located specifically on or near K218b's itself, rather than simply somewhere in that general direction of the sky, any signal it produced should exhibit a specific, predictable pattern of Doppler shift, a subtle change in frequency caused by the planet's own orbital motion toward and away from Earth as it circles its star. By observing across a full orbital period, the research team gave themselves the ability to check any candidate signal against this expected pattern, filtering out signals that didn't match the planet's actual physical motion. A powerful tool for distinguishing a signal that might genuinely originate from the K218 system itself from the enormous amount of radio interference and background noise that otherwise fills the sky, and there is an enormous amount of noise to filter through. Modern radio telescopes operating at this level of sensitivity don't detect a handful of interesting signals and a lot of quiet emptiness in between. They detect an overwhelming flood of data, the vast majority of it either naturally occurring astrophysical noise or, far more commonly, radio frequency interference, abbreviated RFI, generated by human technology here on Earth, cell phone towers, satellites, television broadcasts, radar systems, and countless other sources of artificial radio emission that our own planet constantly produces, whether we intend to or not. Ironically, the single biggest technical challenge in searching for someone else's artificial radio signals turns out to be filtering out the overwhelming quantity of our own. To manage this, the research team developed and applied what they described as a comprehensive, multi-stage post-processing framework, essentially a carefully constructed filter designed to systematically eliminate false candidates while preserving anything that might represent a genuine signal. The process included several distinct stages. First, removing known contaminated frequency bands where human-generated interference is common and well documented. Second, applying drift rate filtering, checking whether a signal's frequency changed over time in a pattern consistent with the expected orbital dynamics of the K218 system, rather than some unrelated source. Third, using what's called multi-beam spatial discrimination, a technique that compares a signal detected in the beam pointed directly at K218 against signals detected in separate control beams pointed at nearby, unrelated patches of sky, since a genuine signal from K218 itself should appear only in the beam actually aimed at it, while background interference typically shows up across multiple beams simultaneously. Fourth, checking for consistency with the planet's primary and secondary transit behavior, the specific times when the planet passes in front of or behind its host star as seen from Earth, and finally, applying strict signal-to-noise ratio thresholds, discarding any candidate signal too weak or too statistically ambiguous to represent confident evidence of anything at all. The scale of the raw data the team had to process through this filtering framework is genuinely difficult to comprehend. Across all of their observations, the search identified and evaluated millions of individual candidate signals. To test how reliable their filtering process actually was, the team ran a validation experiment, injecting artificial, synthetic signals into their recorded data using specialized software, then running those same synthetic signals through their entire detection and filtering pipeline to see how well the system could distinguish genuine signals from noise. The results of this validation were sobering in their own right. The team found that, on average, nearly 80% of signals meeting a specific signal-to-noise threshold and appearing across relatively short time windows turned out to be false positives, artifacts of noise or interference rather than anything real. This finding alone says something important about the entire field of technosignature research. Something worth sitting with before we get to the final result. Even with extraordinarily sophisticated filtering, the vast majority of everything that initially looks like it might be a signal turns out, on closer inspection, to be nothing at all. After applying this entire 5-stage filtering sequence to every single one of the millions of candidate signals detected across 33 days of observation, spanning both radio facilities and the full range of frequencies studied, the research team's final result was this. No signal survived every stage of the filtering process. No candidate remained that could be confidently attributed to either a natural astrophysical source that didn't already have a known mundane explanation, or, more importantly for the purposes of this search, to any kind of artificial, engineered transmission originating from the K218 system. It's worth pausing here to be very precise about what this result does and does not mean, because this is exactly the kind of finding that gets flattened and distorted the moment it leaves a scientific paper and enters a headline. In an interview given after the study's publication, lead researcher C.D. Tremblay was careful to clarify this point directly, telling one interviewer plainly that the team did not conclude there are no technosignatures associated with K218b. That's a critical distinction, and it's worth understanding exactly why the wording matters so much. A null result in a search like this doesn't prove absence. It establishes a limit, a boundary on how strong any hypothetical signal could possibly be, given that the search didn't detect one. Specifically, the team's non-detection allowed them to calculate what's called an upper limit on the transmitting power of any persistent isotropic radio transmitter that might exist somewhere in the K218 system, arriving at a figure in the range of 1012 to 1013 watts, meaning any transmitter operating below that power threshold. Using the specific narrowband technique the search was designed to detect would have gone completely unnoticed, indistinguishable from the millions of other signals filtered out as noise. To make that number concrete, it's worth comparing it to something we already understand. The Arecibo Observatory in Puerto Rico, before its dramatic structural collapse in December 2020, was for decades one of the most powerful single radio transmitters ever built by humanity, capable of broadcasting planetary radar signals with an effective power in roughly the same general range as the upper limit this new K218b search was able to establish. What this means in practice is this. If a civilization on or near K218b possessed radio technology roughly comparable to the most powerful transmitter humanity has ever built, and happened to be actively, continuously broadcasting in exactly the narrowband frequencies this search examined, during exactly the observation windows when Earth's telescopes happened to be listening. The search would likely have been sensitive enough to detect it. Any signal weaker than that, using a different transmission strategy, occurring at a different time, or using a fundamentally different technology than the kind of narrowband radio beacon this search was specifically designed to find, would have passed through completely undetected. This is worth sitting with for a moment, because it reveals something important about the actual scope of what a single techno-signature search, however sophisticated, can genuinely rule out. Consider everything that would need to be true simultaneously for this search to have had any realistic chance of success. A civilization would need to exist in the K218 system in the first place. That civilization would need to have developed radio technology at all, a specific and, on Earth's own timeline, extremely recent technological milestone developed only within roughly the last century and a half of a planet that has hosted life for well over 3 billion years. That civilization would need to be actively transmitting, rather than simply possessing the technology without using it for interstellar signaling. That transmission would need to be narrowband rather than broadband, matching the specific kind of signal this particular search technique was designed to detect. And that transmission would need to have been happening, and aimed in a direction where Earth's telescopes could pick it up. During precisely the 33-day observation window this particular study happened to occupy, out of the entire multi-billion-year history of that star system. This is the sobering mathematics that sits underneath every SETI search ever conducted, not just this one, and it's a theme we've touched on before on this channel in relation to the Fermi paradox. A null result from a single, even a very thorough and well-designed search, tells us far less about whether intelligent life exists somewhere than it tells us about how narrow and specific the conditions for detection actually are. We are not simply asking, is anyone out there? We are asking a much more restrictive question, is anyone out there, using this specific technology, transmitting in this specific way, pointed in this specific direction, during this specific narrow window of time, measured against a search capability that, however impressive by human standards, still can only detect transmitters above a certain minimum power threshold. Every NOAA search like this closes off only one small, specific slice of an almost incomprehensibly large space of possibilities. And yet, despite all of these limitations, and despite the fact that the search ultimately found nothing, the research team, and much of the broader scientific community responding to their work, has described this study as a genuine, meaningful step forward for the field. For reasons that have less to do with K218b specifically, and more to do with the methodology the team developed along the way. Both the VLA and MeerKAT observations relied on specialized back-end systems built specifically for this kind of high-throughput techno-signature search. The VLA search used a system called COSMIC, the Commensal Open Source Multimode Interferometer Cluster, which allows the array to conduct a dedicated SETI search simultaneously alongside whatever other scientific observations the telescope happens to already be conducting for other researchers, effectively getting technosignature search time essentially for free, riding alongside the observatory's existing fully booked observing schedule rather than competing for dedicated, separately funded time. The MeerKAT observations used a parallel system called BLUES, the Breakthrough Listen user-supplied equipment, connecting the South African array into the broader Breakthrough Listen initiative, a decade long. Privately funded SETI research program launched in 2015 with significant financial backing from the Breakthrough Initiatives Foundation, representing one of the most ambitious, best-funded searches for extraterrestrial intelligence ever undertaken. This commensal approach, piggybacking a technosignature search onto observing time that was already going to happen anyway for other scientific purposes, represents a genuinely important shift in how SETI research operates day to day. For much of the field's history, dating back to its earliest projects in the 1960s, SETI research has struggled with a fundamental resource problem. Dedicated radio telescope time is scarce, enormously expensive, and in high demand from astronomers studying pulsars, galaxies, and countless other legitimate scientific targets. Meaning any hours spent specifically searching for alien radio signals were, in a very real sense, hours not spent on other established, more immediately productive lines of astronomical research. The commensal model developed and refined through this K218b search, and through Breakthrough Listen's broader infrastructure more generally, sidesteps the competition almost entirely, allowing technosignature searches to happen continuously in the background without requiring their own dedicated, separately justified block of expensive telescope time. Equally significant is the analytical framework the team built to process the resulting flood of data, the same 5-stage filtering pipeline we walked through earlier, refined and validated using the synthetic signal injection tests described in the paper. Modern radio telescope arrays like the VLA and MeerKAT generate staggering quantities of raw data, far more than any team of human researchers could ever hope to sort through manually, signal by signal. The processing framework this study developed, and the specific validation methodology used to characterize its false positive rate, represents a template that future searches toward other promising exoplanets can adopt and build on directly, rather than each individual research team needing to reinvent the entire analytical pipeline from scratch. In this sense, even though the specific search toward K218b came back empty, the tools built to conduct that search represent a durable, reusable scientific asset, one that makes every subsequent search toward K218b or toward any other target faster, more sensitive, and more reliable than it otherwise would have been. This is worth connecting back to something we discussed earlier this year on this channel in relation to the broader Fermi paradox. The deceptively simple question posed by physicist Enrico Fermi in 1950, if the universe is so vast and so old and contains so many stars and, as we now know, so many planets, then where is everyone? One of the proposed resolutions to that paradox involves what's sometimes called the search problem itself. The idea that even if intelligent, technological civilizations are relatively common throughout the galaxy, actually detecting one requires an almost impossibly precise alignment of factors. The right target, the right frequency, the right technology, the right moment in time, all converging simultaneously out of a search space so large that even our most ambitious current efforts have only ever managed to examine an infinitesimally small fraction of it. The K2-18b search, however well designed, however methodologically sophisticated, searched exactly one star system across roughly 33 days within one relatively narrow band of the electromagnetic spectrum out of a galaxy containing an estimated 100 to 400 billion stars, the overwhelming majority of which have never been examined by any technosignature search at all in any frequency range for even a single day. It's worth introducing, at this point, a framework astronomers have used for over 60 years to try to think systematically about exactly this kind of question, because it helps explain why a single null result, however well executed, was never going to settle anything on its own. In 1961, astronomer Frank Drake proposed what's now known as the Drake equation, a formula intended not to produce a precise, confident answer, but to organize the problem of estimating the number of detectable civilizations in our galaxy into a series of individually smaller, more tractable questions. The equation multiplies together a chain of factors: the rate of star formation in the galaxy, the fraction of those stars that have planets, the average number of planets per star capable of potentially supporting life, the fraction of those planets where life actually develops, the fraction of that life that evolves into intelligence, the fraction of intelligent life that develops detectable technology, and finally, the average length of time such a civilization continues broadcasting detectable signals before falling silent, whether through extinction, technological shift, or simply choosing to stop. The honest, somewhat humbling truth about the Drake equation, more than 60 years after Frank Drake first proposed it, is that we still have only the loosest possible grip on most of these individual variables. We've made genuine progress on some of them, thanks to missions like Kepler and, more recently, jwst itself. We now have solid statistical evidence that planets are common, that a meaningful fraction of stars host worlds within their habitable zones, numbers that were pure speculation when Drake first wrote his equation down. But we remain almost completely in the dark on every term further down the chain. How often life actually originates given the right conditions. How often it evolves toward intelligence rather than remaining simple and microbial indefinitely, as it did on Earth for roughly 3.5 billion of our own planet's 4.5 billion year history. How often intelligence leads specifically to detectable technology, and, perhaps most uncertain of all, how long any civilization continues broadcasting once it develops the capability to do so. Depending on which reasonable estimates you plug into that final term alone, the Drake equation can output answers ranging from "we should be practically swimming in detectable civilizations" to "we may well be entirely, permanently alone in this galaxy," using nothing more than differently reasonable assumptions applied to the exact same basic framework. This is precisely the uncertainty that makes searches like this week's K2-18b study so valuable despite returning nothing. And it's worth stating plainly why. Every technosignature search that comes back empty, whatever else it fails to prove, does something quietly important. It incrementally, if only slightly, constrains the plausible range of values for those later. Most uncertain terms in Drake's equation, particularly around how many civilizations might currently be broadcasting detectable radio signals using the specific kind of technology we know how to search for. It's a slow, unglamorous process of elimination, star system by star system, frequency band by frequency band, each individual null result adding one more small, specific data point to an otherwise almost entirely theoretical calculation. It will likely take not one search, not 10 searches, but potentially thousands or tens of thousands of searches like this one, spread across a meaningful fraction of the galaxy's hundreds of billions of stars, before the accumulated body of null results starts to meaningfully narrow humanity's honest uncertainty about how common or rare we actually are. It's worth pausing here to talk about a piece of SETI history that captures exactly why researchers have learnt to be so methodologically careful, so resistant to declaring victory prematurely, even when a signal briefly looks extraordinarily promising. On August 15th, 1977, an astronomer named Jerry Ehrman, working at Ohio State University's Big Ear Radio Telescope, was reviewing a printout of recorded data when he noticed an extraordinarily strong narrowband signal lasting a full 72 seconds, matching almost exactly the theoretical profile scientists had long predicted an artificial interstellar beacon might produce. Ehrman was startled enough by what he saw that he circled the relevant sequence of characters on the printout and wrote a single word beside it in red ink: "Wow." The signal, which came to be known ever since as the WOW signal, remains, to this day, one of the strongest and most tantalizing candidate detections in the entire history of SETI research. And yet, despite decades of follow-up observations, using increasingly sensitive instruments pointed at the exact same patch of sky, the WOW, signal has never been detected again, not once, in the nearly 50 years since that August night. Numerous natural explanations have been proposed over the years, including a passing comet releasing a burst of hydrogen gas, coincidentally aligned with the telescope's field of view at exactly the right moment, though this and other proposed explanations remain genuinely contested, with no single account winning broad, confident scientific consensus even today. The signal exists, permanently, in a strange, unresolved limbo, real, recorded, undeniably detected exactly once, and never adequately explained, never confirmed as artificial, and never repeated. The WOW signal illustrates precisely the kind of caution embedded in the 5-stage filtering process used in this week's K218b search, and in virtually every rigorous SETI methodology developed in the decades since 1977. A single detection, however striking, however narrowband, however seemingly consistent with what an artificial beacon should look like, is not enough. Real scientific confidence requires repeatability, requires a signal that can be independently confirmed across multiple observations, multiple instruments, and ideally multiple independent research teams, precisely because the history of the field is littered with individually compelling, ultimately unconfirmed candidate signals that excited researchers in the moment and then simply vanished under further scrutiny. Exactly the kind of outcome the K218b team's synthetic signal injection testing was specifically designed to guard against in advance. There's a similarly instructive, more recent example worth mentioning as well. In 2019, researchers using data from the Parkes Observatory in Australia detected an intriguing narrowband signal that appeared to originate from the general direction of Proxima Centauri, the closest star to our own Sun. A signal that briefly generated considerable excitement within the SETI research community and, once details leaked to the press in late 2020, considerable public attention as well. Named BLC-1, short for Breakthrough Listen Candidate 1, the signal exhibited several properties consistent with what a genuine technosignature might look like. But after extensive follow-up analysis, researchers ultimately concluded that BLC-1 was almost certainly a form of radio frequency interference, likely generated by human electronic equipment somewhere on or near the observatory itself. Its apparent characteristics an artifact of how that specific interference interacted with the telescope's own instrumentation, rather than any genuine signal arriving from interstellar space at all. Both of these examples, the WOW signal and BLC-1, separated by more than 40 years and representing dramatically different eras of technology, point toward the same underlying lesson that shaped how this week's K2-18b search was designed from the very beginning. The universe, and our own planet's own electronics, produce an enormous quantity of momentarily convincing false alarms, and the actual, unglamorous work of SETI research consists overwhelmingly of carefully, systematically ruling those false alarms out, one at a time, rather than the dramatic moment of discovery popular culture tends to imagine. The millions of candidate signals filtered out of this week's K2-18b data, and the roughly 80% false positive rate the team measured in their own validation testing, sit squarely within this same long, humbling tradition, a tradition built almost entirely around the difficult, disciplined practice of saying not yet, and not this, and not proven again, and again, and again, for decades, in the patient hope that someday one particular signal simply won't go away under scrutiny the way all the others always have. It's worth remembering, too, just how recently the instrument responsible for nearly every atmospheric finding discussed tonight actually became operational. jwst launched on December 25th, 2021, following decades of development, delays, and cost overruns that at various points threatened to cancel the project entirely, before finally reaching its observing position roughly 1 million miles from Earth, at a gravitationally stable point called the second Lagrange point, in January 2022. Its first science observations began that summer, meaning every single jwst-derived finding about K2-18b discussed tonight, the 2023 methane and carbon dioxide detection, the 2025 DMs controversy, all of it has been generated within a scientific window barely 4 years old. Given how much genuine uncertainty and disagreement has already emerged from just these first few years of observation, it's worth holding on to some genuine optimism that considerably more clarity in one direction or the other likely still lies ahead as jwst continues operating, as additional observing time gets allocated, and as the broader scientific community continues refining exactly how to interpret data this close to the technical edge of what even our best current instruments can reliably measure. It's a genuinely strange thing to sit with. Nearly everything humanity currently believes, disputes, and doesn't yet know about this one specific. Potentially extraordinary planet has all been learned within a span of time shorter than a single presidential term, using an instrument still, in a real sense, early in its own operational life. Whatever comes next in this story, and something almost certainly will, given how much observing time remains allocated to this one small, stubborn, uncooperative planet, it will very likely arrive sooner than the multi-decade timelines we've grown used to discussing on this channel. A rare case where the next chapter might genuinely unfold within the working lifetime of everyone currently listening. Let's talk for a moment about K218's host star itself, because the fact that it's a red dwarf carries real scientific weight, both for and against the planet's habitability. That's worth understanding in more depth than the simple habitable zone label usually conveys. Red dwarfs, technically classified as M-dwarf stars, are the most common type of star in the entire galaxy, making up an estimated 70 to 75% of all stars in the Milky Way. Smaller, cooler, dimmer, and dramatically longer lived than stars like our own Sun, with lifespans that current astrophysical models suggest could extend for trillions of years, far longer than the current age of the universe itself. This longevity makes red dwarfs, on paper, tantalizing candidates for hosting long-term habitable environments, since a planet orbiting one has, in principle, an enormously long window of stable stellar conditions in which life could potentially emerge and evolve, compared to the roughly 10 billion year total lifespan expected for a star like our own Sun. There's a second complication specific to planets orbiting this close to a red dwarf, separate from stellar flares. That's worth mentioning briefly: tidal locking. Because K218b orbits so close to its host star, completing a full orbit in just 33 days, gravitational forces acting over the system's multi-billion year history have likely locked the planet's rotation to its orbit, the same way our own moon is tidally locked to Earth, meaning one hemisphere of K218b may permanently face its star in perpetual daylight, while the opposite hemisphere remains in permanent darkness. This kind of configuration raises genuinely open questions about atmospheric circulation and temperature distribution. Without Earth's familiar day-night cycle to help distribute heat evenly, a tidally locked planet could develop extreme temperature contrasts between its two hemispheres, potentially affecting where, if anywhere, conditions might remain stable enough to support the kind of chemistry astrobiologists associate with habitability. Some climate models suggest K218b's thick hydrogen atmosphere may be dense enough to redistribute heat effectively despite tidal locking, smoothing out the extremes that a thinner atmosphere would allow. But this too remains an active, unresolved area of ongoing research. One more item on the long list of physical uncertainties that make this planet simultaneously so compelling and so difficult to characterize with any real confidence. But red dwarfs come with a serious complication that has increasingly worried astrobiologists studying planets like K218b. Because these stars are so much dimmer than our own Sun, their habitable zones sit much closer in, as we discussed earlier, close enough that planets within them are often subjected to dramatically more intense stellar activity than Earth ever experiences from our own. Comparatively calm, middle-aged sun. Young red dwarf stars in particular are known for producing frequent, powerful flares, sudden, intense bursts of radiation and charged particles, far more energetic relative to their size than anything our own sun typically produces, capable of stripping away a closely orbiting planet's atmosphere over time, or bathing its surface in levels of ultraviolet and X-ray radiation that could pose serious challenges for the kind of complex surface-based life we're familiar with from Earth. Whether K218b's own host star has historically been active enough to pose this kind of threat to any potential surface habitability remains a genuinely open, actively studied question. Some research suggests K218, at an estimated age of several billion years, may now be in a comparatively quieter phase of its activity cycle, having calmed down considerably from a more violent youth, similar to a general pattern astronomers have observed across red dwarf stars more broadly. But even a quieter, more settled red dwarf sits close enough to a planet in its habitable zone that questions about atmospheric erosion, radiation exposure, and the resulting long-term prospects for a stable, sustained biosphere remain, in the words of multiple research teams that have studied the system, genuinely unresolved, adding yet another layer of uncertainty on top of the atmospheric composition debate, and the fundamental question of what actually lies beneath K218b's hydrogen envelope in the first place. This layered uncertainty, atmospheric chemistry that different research teams interpret differently, a planetary interior that could be a habitable ocean or an inhospitable magma sea depending on which model you trust, and a host star whose historical activity levels remain only partially understood, is worth naming directly because it's easy in the rush toward a satisfying headline. To lose track of just how many independent, still open scientific questions would all need to resolve in exactly the right direction before K218b could be confidently described as habitable, let alone actually inhabited. Each of these open questions represents its own separate area of ongoing research, its own separate set of scientific papers, its own separate community of specialists working to narrow the uncertainty, and none of them, as of this week, has been definitively closed. Let's spend a few minutes building an honest sense of what 124 light-years actually means, because, exactly like we've done with other distances on this channel, the number by itself doesn't mean much until you hold it up against something concrete. If New Horizons, the fastest spacecraft humanity has ever launched, currently drifting through the outer solar system at roughly 34,000 miles per hour, were somehow redirected toward K218, it would take the spacecraft well over 2 million years to arrive, a span of time that dwarfs the entire history of our own species. Anatomically modern humans have existed for perhaps 300,000 years, meaning New Horizons would need to travel for nearly 7 times longer than our entire species has existed, just to reach a planet we've now spent 2 full years arguing about, using nothing but light that already made that same trip, unaided, in a little over a century. Even a hypothetical, far more advanced propulsion system changes this calculation less than you might hope. We discussed on a previous episode of this channel the breakthrough starshot concept, a proposed system using ground-based lasers to accelerate small lightweight probes to roughly 20% of the speed of light, fast enough to reach Alpha Centauri, our nearest star system at 24 light-years in a little over 20 years. Applying that same theoretical speed to K218's distance of 124 light-years, nearly 30 times further than Alpha Centauri, a Starshot-style probe would still need approximately 620 years just to complete the one-way journey, and then, exactly like every deep space mission we've discussed before, another 124 years for any data the probe managed to collect to travel back to Earth at the speed of light. A message sent today, using our absolute best current theoretical technology, would not be answered, if it could be answered at all, until sometime in the 8th century from now, roughly as far into our own future as the founding of the Holy Roman Empire sits in our past. This is, in the end, the real and complete reason radio, rather than physical travel, remains the only remotely practical method by which humanity, or any hypothetical civilization on K218b, could ever hope to actually communicate with each other. Light itself, the fastest thing that exists, still takes 124 years to make the trip. But that's a genuinely small fraction of the multi-thousand-year timescales physical travel of any kind would require, and this fact points directly back to the deeper strangeness sitting underneath this week's entire story. Even in the best possible outcome, even if this search, or some future search, someday did detect a genuine, confirmed artificial signal coming from K218b, we would still be receiving a message that was sent 124 years ago from a civilization, if one exists there at all, that has already continued living an additional 124 years beyond whatever moment that signal actually left their world. Any reply we sent back would arrive a further 124 years after that, meaning a single, complete round-trip exchange, one message and one response, would span 248 years, longer than the entire history of the United States as a nation. Whatever conversation might theoretically begin between Earth and K218b's would necessarily unfold across a span of time longer than any single human life, likely longer than the memory of the specific individuals who sent the original message on either end. A conversation conducted not between two civilizations existing in any shared present moment, but between two civilizations relating to each other entirely through messages arriving from what is, by the time they're received, already a fairly distant past. It's worth stepping back to place K218b within the broader context of exoplanet research more generally, because it's easy. Watching headline after headline about this one particular planet, to lose sight of just how many other worlds are simultaneously under similar scrutiny. Since the first confirmed detection of a planet orbiting a sun-like star in 1995, astronomers have identified and confirmed more than 5,000 exoplanets, with thousands of additional candidates awaiting confirmation, discovered primarily through two main techniques: the transit method we discussed earlier, watching for the tiny dip in a star's brightness as a planet crosses in front of it, and the radial velocity method, measuring the subtle gravitational wobble a planet induces in its host star as they both orbit their shared centre of mass. Of these thousands of confirmed worlds, only a relatively small subset are considered potentially Hycean, sharing K218b's specific combination of size, orbital distance, and atmospheric composition consistent with a possible hydrogen-blanketed ocean world. Other notable Hycean candidates currently under study include TOI 270d, a sub-Neptune orbiting a red dwarf star roughly 73 light-years from Earth, which jwst observations have also found to contain methane and carbon dioxide in a pattern broadly similar to K218b, without the same disputed DM signal complicating its story, and LH 1140b, a slightly smaller, more rocky candidate located about 49 light-years away, considered by some researchers to be an even more promising target for future atmospheric study, specifically because its somewhat smaller size and cooler host star may make a genuinely rocky, ocean-covered surface more physically plausible than the more ambiguous case presented by K218b's own larger, more gas-enveloped structure. The existence of multiple candidate Hycean worlds, rather than just one unusual outlier, matters scientifically because it suggests this entire category of planet, however strange and however different from anything in our own solar system, may represent a genuinely common outcome of planet formation throughout the galaxy, rather than some unique, one-off curiosity. This growing list of candidates is also precisely why the methodological work done in this week's K218b technosignature search carries value well beyond this one specific planet. The same cosmic and blues backend systems and the same 5-stage filtering framework built and validated through the study can be, and very likely will be, pointed at TOI 270d at LHS 1140b, and at whatever additional Hycean or otherwise promising candidates continue emerging from ongoing survey work, without needing to rebuild the entire analytical infrastructure from scratch each time. In this sense, this week's null result toward K218b specifically represents not an ending, but closer to a calibration step, a first full-scale test of a search methodology built to be reused again and again against an ever-growing list of promising targets as the broader catalogue of potentially habitable worlds continues to expand. And that catalogue is in fact expanding rapidly, driven by a new generation of astronomical instruments either recently operational or scheduled to come online in the coming years. The European Space Agency's Plato mission, short for Planetary Transits and Oscillations of Stars, launched in 2026 and specifically designed to identify Earth-sized planets in the habitable zones of Sun-like stars, a category of world current instruments have struggled to detect reliably, since Earth-sized planets produce a far smaller, far more difficult to measure transit signal than the larger sub-Neptunes like K218b that have dominated habitable zone discoveries so far. NASA's Nancy Grace Roman Space Telescope, expected to launch in the late 2020s, will conduct wide-field surveys capable of detecting exoplanets through a completely different technique called gravitational microlensing, potentially revealing entire populations of planets, including free-floating rogue planets untethered to any star at all that current transit and radial velocity methods simply cannot detect. And looking further ahead, concepts like NASA's proposed Habitable Worlds Observatory, still in early planning stages, aim to be the first telescope purpose built specifically to directly image, rather than merely infer through transit spectroscopy, the atmospheres of potentially habitable, Earth-sized worlds around nearby stars. A technological leap that would represent a qualitative step change from everything discussed so far tonight, moving from indirect, noisy chemical inference to something approaching a genuine, direct look. Each of these upcoming instruments, and the many others currently in development at space agencies around the world, will add to a rapidly growing catalogue of potentially habitable worlds, each one a new candidate for exactly the kind of dual investigation, atmospheric analysis paired with radio technosignature search that has defined K218b's story over the past several years. It's entirely possible, even likely, that within the next decade, this channel will be telling a very similar story about an entirely different planet, one not yet discovered, orbiting a star whose name none of us currently know, using instruments not yet finished being built. K218b, in this sense, isn't the final word on any of these questions. It's simply the current, most prominent test case for a search methodology and a broader scientific process that is still very much in its early stages, with every reasonable expectation of dramatic improvement in the years directly ahead. This is a theme we've returned to again and again on this channel, in the context of Voyager, in the context of New Horizons, and now here again, in the context of a planet we've never visited, and realistically, on anything resembling current or foreseeable technology, never will. Distance in space isn't simply a matter of far versus near. It's a matter of time itself becoming a kind of barrier, a gap that light, the fastest possible messenger, cannot close quickly enough to allow anything resembling a normal conversation. Even between two civilizations that both, hypothetically, want very badly to talk to each other, there's something worth sitting with, in closing, about what it actually means that a team of scientists spent 33 days, an entire orbital year, on a planet 124 light-years away, patiently listening for a signal they had every statistical reason to expect they wouldn't find, and then, having not found one, described the effort as valuable anyway. It would be easy to read a story like this one as simply another disappointment, another entry in a long, unbroken list of searches that turned up nothing, another reminder of just how thoroughly alone the universe can feel from where we're standing. But that reading misses something important about what actually happened this week, and about what this kind of research represents more broadly. Every technosignature search ever conducted, this one included, is built on a specific, quietly optimistic premise that the question is worth asking in the first place, carefully, rigorously, and honestly, even knowing that the overwhelming statistical likelihood is a null result. The researchers who spent months designing the filtering framework used in this study, who ran synthetic signal injection tests to characterize exactly how reliable their own methodology actually was, who coordinated observing time across 2 continents and 2 entirely separate radio observatories, did all of that work fully aware that the most probable outcome was silence. They did it anyway, not because they expected this specific search to succeed, but because the only way any search ever will succeed, someday, on some future target, orbiting some other star, is if researchers keep doing this kind of careful, patient, methodologically honest work, search after search, null result after null result, building the tools and the track record that will eventually make a genuine detection, whenever and wherever it finally happens, actually credible rather than just another wow. Signal that quietly fades back into uncertainty. This is, in its own way, one of the more genuinely admirable things happening quietly in the background of modern astronomy. Easy to overlook amid flashier headlines about possible alien oceans and disputed biosignature gases. A global community of researchers spread across observatories in New Mexico and South Africa, working with data processing frameworks built collaboratively across multiple institutions, continuing to ask the same fundamental question that Kokanai and Morrison first posed in a scientific paper back in 1959. Refining the tools, narrowing the uncertainty, one star system and one null result at a time, sustained not by any expectation of quick success, but by the simple, durable conviction that the question itself, is anyone else out there, deserves to be asked as carefully and as honestly as our current technology allows. It's worth taking a moment to appreciate exactly how recent all of this capability actually is, because it changes how we should think about the search's null result. The Kepler Space Telescope, which first identified K218b's star system as containing a planet of interest, launched in March 2009 and operated using an extraordinarily precise photometer capable of detecting the minuscule dimming caused by a planet crossing in front of its star from millions of miles away. A level of measurement precision that simply didn't exist in any previous generation of astronomical instrumentation. Before Kepler, the search for planets around other stars relied primarily on the radial velocity method, which is inherently biased toward detecting large, massive planets orbiting close to their stars, the kind of worlds capable of producing a measurable gravitational wobble. Kepler's transit-based approach opened the door to detecting smaller, more Earth-like and sub-Neptune-sized worlds for the first time. And by the time the original mission concluded in 2018, having identified over 2,600 confirmed exoplanets, it had fundamentally transformed our understanding of how common planets actually are throughout the galaxy, revealing that, on average, most stars in the Milky Way likely host at least one planet, a conclusion that seemed far from obvious before Kepler's data made it clear. K218b itself was actually discovered during an extended phase of the Kepler mission called K2, launched after a mechanical failure in 2013, disabled 2 of the spacecraft's 4 reaction wheels. The gyroscope-like devices used to precisely orient the telescope in space. Rather than ending the mission entirely, engineers devised a clever workaround, using the subtle pressure of sunlight itself, striking the spacecraft's solar panels, to help stabilize its orientation well enough to continue useful observations, allowing Kepler to survey new patches of sky it hadn't originally been designed to study, including the specific field containing K218. In this sense, the planet at the centre of this entire story, and this week's search for any hint of civilization there, was only ever discovered in the first place, because a spacecraft experienced a partial mechanical failure, and engineers on the ground found a creative, resourceful way to keep it working anyway. A small, but genuinely important reminder that scientific progress often depends as much on this kind of improvisational persistence as it does on any grand original mission design. There's one more concept worth introducing before we close, because it connects everything discussed tonight: the atmospheric uncertainty, the disputed biosignature, the empty radio search, back to the broader question this channel keeps returning to about our place in the universe. Some researchers studying the Fermi paradox have proposed the existence of what's sometimes called the Great Filter, a hypothetical barrier somewhere along the evolutionary or technological path from simple chemistry to a galaxy-spanning civilization that prevents the overwhelming majority of life from ever reaching the kind of detectable, long-lasting technological state that a search like this week's K2-18b survey is actually capable of finding. The unsettling part of this idea isn't simply that such a filter might exist, but that we currently have no way of knowing whether humanity has already safely passed through it, somewhere in our own deep evolutionary past, or whether it still lies somewhere ahead of us, an obstacle our own civilization hasn't yet encountered. If the Great Filter sits behind us, if the truly difficult, improbable step was simply the origin of life itself, or the transition from simple to complex cells, or the emergence of intelligence, then civilizations like our own, once they exist, might reasonably be expected to survive and continue broadcasting for very long spans of time. And the fact that we've detected nothing yet would simply reflect how early we still are in a search that has, in the grand scheme of the galaxy's history, barely begun. But if the filter lies ahead of us, if something about the transition from a technological radio-capable civilization to a longer-term, stable, galaxy-spanning one turns out to be extraordinarily difficult or dangerous, self-inflicted extinction through war or environmental collapse, an unavoidable technological catastrophe, some other barrier we haven't yet identified or even imagined, then every null result from every search like this one carries a slightly different, more uncomfortable implication. Not simply that we haven't found anyone yet, but that perhaps very few civilizations, anywhere, ever survive long enough to be found at all. This is not a question this week's K2-18b search or any single search can answer. It's not a question any realistic amount of searching over any realistic span of time may ever definitively answer, one way or the other. But it's worth naming directly here, because it's the deeper, quieter question sitting underneath every technosignature search ever conducted, the one that makes a null result feel like something more than just an absence of evidence. Every time a search like this one comes back empty, it adds one more small, specific data point to an enormous, ongoing, largely unspoken question about whether civilizations like our own tend to survive, or whether the very fact that we're still here, still asking, still listening, still capable of building instruments sensitive enough to search a planet 124 light-years away, is itself a kind of quiet, statistically improbable achievement that shouldn't be taken for granted. It's worth spending a little more time with the two facilities that actually made this search possible, because both instruments carry their own significant histories, and understanding them helps explain why this particular search was able to achieve the sensitivity it did. The Carl G. Jansky Very Large Array, located on the plains of San Agustin in New Mexico, roughly 50 miles west of Socorro, has been in continuous operation since 1980 and takes its name from Karl Jansky, the Bell Labs engineer who in 1932 made the accidental discovery that launched the entire field of radio astronomy, detecting a persistent radio signal that he eventually traced back to the centre of our own Milky Way galaxy, the first confirmed detection of radio waves from beyond Earth. The VLA itself consists of 27 individual dish antennas, each 25 metres in diameter, mounted on railway tracks that allow the entire array to be physically reconfigured into different arrangements, ranging from a compact cluster just over half a mile across to a sprawling configuration spanning more than 22 miles, depending on the specific resolution and sensitivity requirements of whatever observation is being conducted. This physical reconfigurability is part of what makes the VLA such a versatile instrument, equally capable of studying distant galaxies, mapping the structure of our own galaxy's magnetic field, tracking asteroids, and, as demonstrated this week, searching nearby star systems for any hint of artificial radio transmission. The MeerKAT array, by comparison, is a considerably newer instrument, officially inaugurated in 2018 in South Africa's remote, radio-quiet Northern Cape region, an area deliberately chosen for its extremely low levels of human-generated radio interference, making it one of the best possible locations on the planet for exactly the kind of extremely sensitive listening this search required. MeerKAT's 64 dishes, each 13.5 metres in diameter, were specifically engineered as a precursor and testbed for an even larger, more ambitious project currently under construction in the same region. The Square Kilometre Array, an international collaboration involving dozens of countries that once complete is expected to become the most sensitive radio telescope ever built. With a total collecting area, once fully assembled, covering roughly 1 square kilometre, thousands of times more sensitive than any radio telescope currently in operation. MeerKAT itself already represents one of the most capable radio observatories on Earth, and its integration into the Breakthrough Listen Initiative's search infrastructure means that South Africa, a country that didn't operate any major radio astronomy facility of international significance before MeerKAT's construction, now sits at the very forefront of humanity's search for extraterrestrial intelligence. The fact that this week's search combined data from facilities on 2 different continents, coordinated across international research institutions, funded through a mixture of public astronomical infrastructure and private philanthropic investment through the Breakthrough Initiatives Foundation, says something worth noting about how this kind of ambitious, uncertain scientific work actually gets accomplished in practice. No single country and no single funding source currently possesses enough dedicated resources to conduct searches at this level of sophistication entirely on its own. The K218b technosignature search represents, in miniature, the same kind of broad, patient, internationally distributed collaboration that has characterized the entire modern era of large-scale astronomical research, from the Event Horizon Telescope's imaging of Sagittarius A, which we discussed on a previous episode of this channel, to the James Webb Space Telescope itself, a joint project between NASA, the European Space Agency, and the Canadian Space Agency. The search for life beyond Earth, it turns out, however solitary and quiet the actual results, is very much a collective, global undertaking, built one collaborative search, one shared dataset, one jointly developed analysis framework at a time. It's worth understanding, too, exactly what would need to happen if a search like this one ever did produce a genuinely promising candidate signal, because the process is considerably more rigorous and considerably slower than most popular portrayals of alien contact suggest. The SETI research community has, for decades, operated under a loose but widely respected framework sometimes called the Rio scale, and a related set of post-detection protocols, originally drafted in the 1980s and refined multiple times since, outlining exactly what steps researchers should take if they ever detect a signal that survives all of their initial filtering and analysis. The very first step, before any public announcement, before any celebration, is independent verification, contacting other radio observatories capable of observing the same patch of sky and asking them to attempt to detect the exact same signal, using entirely separate equipment, separate researchers, and separate analysis methods. A signal that only ever appears in one telescope's data, no matter how promising it initially looks, cannot be considered confirmed, precisely because of examples like the WOW. Signal and BLC-1 discussed earlier, both of which were real, recorded detections that nonetheless failed this most basic test of independent reproducibility. Only after a signal survives this kind of rigorous, multi-observatory, multi-team verification process would the broader scientific community, and eventually the public, typically learn about it in any confirmed, credible way. A process that could reasonably take anywhere from several days to several months, depending on the complexity of the signal and the availability of other telescopes. Capable of attempting a follow-up observation. This deliberately slow, cautious process stands in fairly stark contrast to how these stories often get portrayed in popular media, where a single detection tends to be treated as immediate, unambiguous proof, announced within hours and confirmed within the same news cycle. The actual practice of SETI research, exactly like every other branch of rigorous observational science, treats a single detection as nothing more than the beginning of a much longer, much more careful process of confirmation. A process this week's K218b search never even had the opportunity to begin, since no candidate signal survived long enough within the search's own internal filtering process to warrant that kind of external follow-up in the first place. This is worth remembering the next time a headline announces a promising new candidate signal from some other star system, whenever and wherever that eventually happens, because it almost certainly will at some point, given how many searches like this one are now actively running continuously across multiple observatories, scanning an ever-growing list of promising targets. The very first report of any interesting signal should be read, appropriately, as exactly that, an interesting first report, not a confirmed discovery, deserving genuine attention and careful follow-up, but not yet deserving the kind of certainty that would justify declaring, with confidence, that humanity has finally found what it's been listening for since 1959. Let's take a moment to build a clearer physical picture of K218b itself, because the abstract numbers, 2006 times Earth's radius, 8 and 6 times Earth's mass, only start to mean something once you translate them into something closer to a mental image. If Earth were the size of a standard basketball, K218b, scaled proportionally, would be roughly the size of a beach ball, noticeably larger, but still recognisably in the same general category rather than belonging to an entirely different scale of object, the way Jupiter or Saturn would if you tried the same comparison. Its surface gravity, factoring in both its larger size and its greater mass, is estimated at somewhere around 1.3 times that of Earth, meaning a person. If they could somehow stand on whatever surface or transitional layer exists beneath its atmosphere, would feel meaningfully heavier than on Earth, but not so much heavier that the difference would be immediately disabling, roughly comparable to the difference between your normal body weight and carrying a fully loaded backpack. The much harder part to visualize is the hydrogen atmosphere itself, and why its sheer thickness matters so much to every question we've discussed tonight. Earth's atmosphere, by comparison, is remarkably thin. If you shrank Earth down to the size of an apple, the entire breathable atmosphere would be thinner than the apple's own skin. K218b's hydrogen envelope, by contrast, is believed to extend much further relative to the planet's overall size, and critically, hydrogen itself behaves very differently from Earth's nitrogen-oxygen atmosphere as you descend deeper into it. As you travel downward through a thick hydrogen envelope like the one K218b likely possesses, both temperature and pressure increase dramatically and continuously, with no clear, distinct boundary marking where atmosphere ends and surface begins, the way there is on a rocky world like Earth or Mars. This is precisely why the question of what actually exists beneath K218b's visible atmosphere remains so genuinely contested, unlike a rocky planet, where a surface is a physically obvious, easily defined boundary. K218b's may not have anything resembling a clean, walkable surface at all, but rather a smooth, continuous transition from thick gas to a hypothetical liquid ocean layer to potentially even higher pressure, higher temperature material further down, depending on which of the competing physical models scientists currently favour turns out to be correct. This uncertainty about the planet's basic physical structure is worth holding on to, because it reshapes what a Hycean ocean, if one genuinely exists there, might actually look like, compared to the instinctive mental image the word ocean naturally conjures. It would almost certainly not resemble anything like Earth's oceans, with a clear water surface open to a breathable sky above it. Depending on the exact temperature and pressure profile of K218b's hydrogen envelope, any liquid water layer that exists could be buried beneath enormous atmospheric pressure, sealed under conditions of heat and pressure that would be instantly, catastrophically lethal to any Earth-based life, even if liquid water genuinely persists there in some form. The word ocean, borrowed so naturally from our own planet's experience, may be doing more work in the public imagination than the actual physics of the situation can currently support. A gap between vivid, evocative language and genuinely uncertain underlying science that runs through nearly every part of this story, from the Hycean world label itself to the disputed DM signal to this week's now completed radio search. It's worth reflecting, briefly, on how this specific gap between careful scientific uncertainty and the more dramatic, simplified version of the story that circulates publicly has shaped K218b's entire media life over the past several years, because it's a genuinely useful case study in how science communication succeeds and fails in the modern information environment. Each of the major findings we've discussed tonight, the 2023 methane and carbon dioxide detection, the 2025 DM's announcement, and now this week's radio search, was accompanied in its initial press coverage by headlines considerably more confident and considerably more dramatic than the underlying scientific papers themselves ever claimed to be. The original 2023 research paper describing the Hycean hypothesis was, in the actual language used by Madhusudan's own team, appropriately careful and conditional throughout, describing K218b as a candidate Hycean world, and explicitly noting the very low, roughly 1 sigma confidence level of the initial DM's hint. Much of the accompanying media coverage, understandably chasing public interest in a genuinely exciting possibility, tended to compress that careful, conditional language into simpler, more attention-grabbing framings. Versions of the story that emphasized the exciting possibility of an alien ocean considerably more than the extensive uncertainty surrounding it. This pattern repeated itself in a different form with this week's radio search as well. The underlying scientific paper is by design a methodologically dense, carefully hedged document, explicit about its limitations, explicit about the upper limit nature of its conclusions, and explicit, as researcher Tremblay stated directly, that a null result doesn't prove the absence of a civilization. And yet the very same finding can easily be, and often has been, compressed into a much simpler public narrative. Scientists searched for aliens and found nothing. A technically accurate but meaningfully incomplete summary that loses almost everything about what the search actually demonstrated, what its real limitations were, and why the research team themselves considered the effort valuable despite, and in some ways because of, its null result. None of this is a criticism of science journalism as a whole, much of which does genuinely careful, responsible work translating complex research for a general audience. It's simply worth naming as a pattern, because it shapes how a story like K218b's continues to circulate and mutate as it moves further from the original source material, and because understanding that pattern is part of understanding the full, honest picture of what has and hasn't actually been established about this particular, genuinely fascinating world. The real story, the one this video has tried to walk through carefully tonight, sits somewhere between the two extremes, not the confident alien ocean version that periodically goes viral, and not the dismissive, nothing to see here version that sometimes follows a null result, but the actual, considerably more interesting truth. A planet genuinely uncertain enough, genuinely promising enough, to justify years of sustained, serious scientific attention, still keeping its most important secrets, for now, entirely to itself. There's a particular kind of patience required for this entire field of research that's worth naming directly before we close, because it's fundamentally different from the kind of patience most other areas of science demand. A chemist running an experiment can usually expect a result within hours or days. A field biologist tracking a population over years can still expect to see meaningful, visible change within their own working lifetime. SETI research and technosignature searchers like this week's K218b study specifically operate under a genuinely different kind of time horizon, one where researchers spend entire careers, sometimes generations of researchers spend entire careers, building infrastructure, refining methodology, and searching star system after star system, with a very real, statistically honest possibility that success, if it ever comes at all, might not arrive within the working lifetime of anyone currently doing the searching. Frank Drake, who proposed the equation bearing his name back in 1961, continued actively working in SETI research until his death in 2022, spending over 60 years of his own life contributing to a search that, across his entire career, never produced a single confirmed detection. Jill Tarter, another towering figure in the field's history, spent decades directing SETI research at the SETI Institute, famously the inspiration for the lead character in Carl Sagan's novel Contact, and later its film adaptation, dedicating her professional life to a search that, as of this week's K218b results, still has not found what it's looking for. This is worth holding alongside everything else discussed tonight, because it reframes what a null result from this week's search actually represents within the context of a field defined, from its very origins, by exactly this kind of extended, uncertain, patient commitment. Tremblay and the rest of this week's research team are not the first researchers to spend months of careful, rigorous work only to conclude, honestly, that they found nothing. They're simply the most recent entry in a lineage of scientists stretching back over 60 years, each one adding their own small, careful contribution to a search that may take considerably longer than any single human lifetime to resolve, if it resolves at all. And yet the search continues, not despite that uncertainty, but in some sense because of it, because the alternative, simply deciding the question isn't worth asking carefully, feels like a genuine abdication of exactly the kind of curiosity that has driven human beings to build telescopes, launch spacecraft, and stare into the night sky asking questions, for as long as anything resembling human civilization has existed at all. K218b. Whatever it eventually turns out to be, an ocean world genuinely worth the excitement it's generated, a molten, inhospitable furnace dressed up in misleading spectroscopic ambiguity, or something stranger and more unexpected than either current hypothesis anticipates, will very likely remain one of the most closely watched, most carefully studied planets beyond our own solar system for years to come, precisely because it sits so close to the genuine, unresolved edge of what we currently know how to determine about a world we will, in all likelihood, never visit, never see up close, and never know with total certainty, using anything resembling the technology available to us today or in the foreseeable future. It's worth returning one final time to that connection between Jill Tarter's real career and Carl Sagan's fictional depiction of one very much like it, because Sagan himself, whose reflections on the pale blue dot photograph closed out an earlier episode of this channel, understood something about this particular kind of search that feels worth carrying into tonight's closing thoughts as well. In Contact, Sagan's own 1985 novel, the fictional search for extraterrestrial intelligence is portrayed not primarily as a hunt for definitive proof, but as an act of genuine, sustained hope, carried out by people willing to spend entire careers listening carefully to noise, in the patient belief that distinguishing a real signal from all of that noise matters enough to keep trying. Year after year, regardless of how many searches come back empty first. Sagan wrote that novel and delivered his real-world reflections on the pale blue dot photograph from a career spent thinking seriously about exactly the kind of question this week's K2-18b search was built to ask, and his own conclusion, expressed across decades of writing and public communication, was never that the search was naive or unlikely to succeed. It was that the search itself, conducted honestly, carefully, and with appropriate humility about how much remains unknown, was worth doing precisely because so much genuinely does remain unknown, and because the only way to ever change that is to keep looking, keep listening, keep refining the methodology, one star system. One null result, one careful, honest scientific paper at a time. Looking ahead, the research team behind this week's search has indicated that K2-18b remains an active target for continued observation, both in terms of further radio technosignature work, using increasingly refined versions of the same detection framework, and in terms of the atmospheric spectroscopy debate that has run alongside it since 2023. Additional jwst observing time dedicated to K2-18b has already been allocated for further study, aimed specifically at resolving the ongoing disagreement over the DM's and DMD's signal, gathering additional data at the specific wavelengths where the competing research teams' interpretations diverge most sharply, in the hope of finally settling, one way or the other, whether the original tentative detection reflects a genuine atmospheric signal or an artifact of instrumental noise. Given how contested the current data already is, it may take several more rounds of observation, spread across the coming years, before the scientific community reaches anything resembling a stable consensus on this specific question, let alone on the much larger question of whether the planet is genuinely habitable, let alone inhabited. In the meantime, the radio search itself is unlikely to be a one-time event. Breakthrough Listen's ongoing partnership with facilities like MeerKAT means that K2-18 will very likely remain within the broader catalogue of star systems receiving periodic monitoring, particularly as new observing opportunities arise through the same commensal piggyback scheduling model that made this week's search possible in the first place. Should any future observation ever detect a signal that survives the full filtering pipeline this team has now built and validated, the verification process described earlier, independent confirmation across multiple observatories, careful, deliberate, methodical checking would begin immediately, and any resulting announcement would likely unfold over a span of weeks or months, rather than the instantaneous, dramatic reveal popular culture tends to imagine. For now, though, that process remains entirely hypothetical. What actually happened this week was quieter, more provisional, and, in its own careful way, more honest than any dramatic discovery would have been. A team of scientists listened carefully for 33 days to a planet 124 light-years away and heard nothing they could confidently call a voice. There's a particular kind of value in that outcome that's easy to overlook if you're only counting discoveries rather than paying attention to what the process itself reveals. This week's search didn't just fail to find aliens on K218b. It successfully demonstrated, in real working conditions, across 2 continents and 2 independent radio facilities, that humanity now possesses the combined technological capability to point sophisticated instruments at a specific, chosen exoplanet 124 light-years away, filter through millions of individual signals with a rigorously validated, quantified false positive rate, and produce a scientifically meaningful, statistically grounded upper limit on the kind of technology that might exist there. 67 years after Cockney and Morrison first proposed, on paper, that this kind of search might theoretically be possible, it now, demonstrably, actually is, repeatedly, reliably, and with a level of methodological rigour their original 1959 paper could only have imagined. That capability, quietly proven again this week, matters just as much as whatever K218b itself eventually turns out to be, because it's the same capability that will eventually be pointed at TOI 270d, at LH 1140b, and at whatever new Hycean or Earth-like candidate emerges next from Plato, from Roman, from instruments not yet built, carrying with it every lesson, every refinement, and every hard-won piece of methodology this specific, quiet, ultimately empty search toward K218b helped establish. There's something worth sitting with in the simple image at the centre of this entire story, stripped of all the statistical thresholds and filtering frameworks and disputed spectroscopic confidence levels for 33 days, spanning 1 complete year on a planet 124 light-years away, 2 enormous arrays of radio dishes, one scattered across the high desert of New Mexico, one spread across the remote plains of South Africa, sat quietly pointed at the same small patch of sky, patiently recording every whisper of radio energy arriving from that direction, sorting through millions of individual signals in the hope of finding one that didn't belong to us. It's a strange, quietly moving thing to picture, this deliberate, coordinated act of listening, undertaken by people who understood, going in, exactly how unlikely success was, and did the careful work anyway. Not because they expected K218b specifically to answer, but because somewhere, someday, on some world we haven't found yet, orbiting some star whose name we don't yet know, something might. And the only way to ever be ready to recognize that signal when it finally arrives is to keep building the tools, keep refining the methods, and keep listening, carefully, patiently, honestly, to everything the universe happens to be sending our way, whether or not, this particular week, on this particular world, anyone was actually there to send it. That's where we'll leave things tonight, not with contact, and not with certainty, but with a planet still turning quietly in the dark, 124 light-years away, holding on to its own unresolved questions exactly as carefully as it has held them since long before anyone on Earth ever pointed a telescope in its direction. It remains, tonight, exactly what it was before this week's search began, a genuinely fascinating, genuinely uncertain world with confirmed methane and carbon dioxide in its atmosphere, a disputed, unresolved hint of a possible biosignature gas, an interior that might be a warm, habitable ocean, or might be an inhospitable sea of molten rock. And now, as of this week, no detectable evidence of anyone home to answer if we called. None of these findings, individually or together, tell us with any confidence whether life exists there. What they tell us, instead, is something quieter, and in its own way just as significant, that we now possess the technology, the methodology, and the patient, careful scientific culture necessary to actually ask the question properly across 124 light years of empty space, using tools sensitive enough to detect a transmitter as powerful as our own most powerful radio telescope, if one happened to be there broadcasting during the exact 33 days we happen to be listening. Somewhere out there tonight, 124 light years away, a world that might be an ocean, might be a furnace, and might, however faintly, hold something alive, continues turning in the dark, exactly as it has for billions of years, entirely unaware that this week, for 33 days, an entire planet quietly stopped to listen. Whatever K218b eventually turns out to be, the search itself will continue, here and elsewhere, long after this particular result fades from the headlines. That's the nature of this kind of work. Not a single dramatic answer, but a long, patient accumulation of careful questions, asked honestly, one star system at a time, by people willing to spend months of effort on the statistically likely chance of finding nothing at all, simply because the alternative, never asking, guarantees an answer we already know we don't want. Rest well.